Now we are going to talk about some of the reactions of 5-membered ring heterocycles such as Furan, Thiophene, and Pyrrole. First, let's talk about the reaction with electrophiles. In the previous lecture, we knew that the 6-membered ring heterocycles like pyridines are not good at reacting with electrophiles, right? But for the 5-membered ring heterocycles, they are much more reactive because they have more electron density in the ring. Therefore, it reacts much more readily with electrophiles than the benzene. And the chemistry of Pyrrole, Thiophene, Furan dominated by readiness to undergo electrophilic substitution. Okay. Normally, as we mentioned in the third lecture, the substitution will go at the alpha position, but if it is blocked, the beta position can also occur with only slightly slower rate. So if you look at the first example, you have the formaldehyde with the secondary amine, which will generate the iminium ion. In this case, this is the electrophile in the reaction called Mannich reaction, which is electrophilic at the carbon. So in this case, you can use the lone pair on the nitrogen, attacking the electrophile and removing the proton here out as a proton. The reason why it prefers to attack at the alpha position is that when you attack at the alpha position, you will get the intermediate that can delocalize electrons to 3 atoms, so 2 carbons and 1 nitrogen. So this intermediate is much more stable than when you attack at the beta position, because you can delocalize electron at only this carbon and this nitrogen. This alkene part doesn't help at stabilizing at all. That's why the alpha attack is more preferred than the beta attack. The reactivity towards electrophile of Pyrrole, if you compare with the benzene type, it is like you already have the electron donating group already installed in your ring of the lone pair of the nitrogen. Is comparable to that of aniline, which is quite nucleophilic and quite reactive towards electrophile. However, the major difference between Pyrrole and aniline is that the ability for the heteroatom itself to react with electrophile. For Pyrrole, we know that the nitrogen needs to give 2 electrons in the pi system in order to make the Pyrrole becomes aromatic with 6 pi electron. If you give this lone pair to some electrophile, this nitrogen will become sp3, and therefore you lose the aromatic system in the Pyrrole ring. If you compare this with pyrrolidine, for example, the nitrogen itself already sp3, and the lone pair is very active. It can give electron to some acid or electrophile quite easily. For the for aniline, this lone pair is less reactive than that of pyrrolidine, because some of it can delocalize into the aromatic system. However, still it can react with electrophile to become sp3. You will lose the stabilization by delocalizing into the ring. However, the ring itself still remains aromatic. So the aniline can easily protonate it, unlike the Pyrrole that cannot protonate at all. However, you can react at the nitrogen by removing the proton here with a strong base. For example, if you use N-butyl lithium, you can remove the proton and generate N anion here, which is now nucleophilic. This one can react with various electrophilic species. For example, this silyl chloride attack here, kick out chloride, and you form the N-substituted product. You don't need to use a very strong base. If you use strong base, you will form the completely deprotonated product. But if you use a weaker base, for example, the DMAP, which is some kind of like pyridine, a very weak base, you will form the anion in a very small amount in the equilibrium. But this small amount can react with electrophile, and then it will eventually shift the reaction due to the irreversible step here. It will shift the equilibrium towards the product. Now let's come back to the electrophilic aromatic substitution at the carbon system. We know that Pyrrole, Furan, Thiophene can react with electrophile at the alpha position as a major compound. But if you compare the rate between the reaction of Pyrrole, Furan, and Thiophene, you will notice that for Pyrrole the rate is much higher, and this is because two effects. First is the greater electron releasing ability of the nitrogen, as you can see in the basicity of, for example, if you compare between saturated amines, ether, and sulfide, the amine lone pair is much more readily available. And another effect is the greater stability of the positive charge on the nitrogen. Therefore, this leads to the more reactive Pyrrole towards electrophile compared to other heterocycles. We have mentioned that for 5-membered ring heterocycle, it will prefer the alpha attack with the electrophile. However, we also need to consider the effect of substituent, especially for the one that has high effects. For example, auto para director like methoxy group, for example, this one has lone pair that can delocalize electron to here and also to here. So if you combine the effect with the alpha attack of the heterocycle, you can see that this position is the major position that electrophile will attack. However, for strong meta directors, for example, a nitro group, we know that it can remove electrons from the ortho and para position to it. So these two positions has lower electron density. And from the knowledge of heterocycles, we know that the alpha effect, the alpha position is preferred, but not that much. If it's blocked, then the beta position is also okay to attack as well. That's why it will go to the beta position here in this case. If the ortho para director is at the beta position now, you can see from drawing the resonance structure, it will only delocalize to this side. On the other side, you cannot delocalize electron to it. That's why if you combine with the effect of heterocycles, this one would be the major attack. For meta director, it at the beta position, it is similar to the previous one because you can only delocalize electron from this position. So this one has less electron density, and the other side is not affected. So due to the alpha preferable to attack at the alpha position of the heterocycle, this position will be preferred to attack with the electrophile. So far we have talked about the reaction between 5-membered ring heterocycles with electrophile in the electrophilic aromatic substitution manner, where the proton will deprotonated here at this step to regain the aromatic system. And this is very common for both Pyrrole and Thiophene. However, For furan, instead of removing proton, sometimes if you have strong enough nucleophile, it tends to attack at the oxonium species here to generate the 2,5 addition product. You can see this product is not aromatic anymore, right? However, for furan, if you remember the first lecture, we talked that if you compare between thiophene, pyrrole, and furan, the aromatic character increase. So the thiophene has the highest aromatic character. This is because sulfur has the lowest electronegativity and oxygen has high En. That's why there's a lot of polarization and the aromatic system is not as stable as thiophene. So for furan, in some cases, you don't need to regain the aromatic system, and sometimes you get the 2,5 substituted, 2,5 addition product of electrophile and nucleophile instead.